Have you ever stopped to wonder how you can open a super heavy door with just a light push? Or, how a little kid can balance someone twice their size on a seesaw? Well, the secret is this amazing invisible force called torque. And today we're going to break down exactly how it makes our world turn.
So let's kick things off at the playground with a puzzle you've probably solved 100 times without even thinking about the physics behind it.
It kind of seems like it defies gravity, doesn't it? I mean, how can your weight possibly balance out someone who's much, much heavier? It's not magic, I promise. It's just really cool physics.
See, the secret here isn't just about how much you weigh. It's all about where you apply that weight. The real key is the distance from that pivot point in the middle, the fulcrum, as physicists call it. It's this beautiful balancing act between your mass and how far you are from the center.
And that balancing act, well, that's what we call torque. Really, at its heart, torque is just a twisting force. It's the oomph you give something to make it rotate. But here's the crucial part. It's not just any old push or pull. It has to be a push or pull that causes something to spin.
Okay, so now that we've got the basic idea down, let's actually put it into practice. We're going to solve a couple of classic balance problems to make sure this concept really sticks.
All right, here's our first little challenge. Imagine a simple meter stick balanced on a fulcrum. On one side, we've got a 200-gram mass that's sitting 20 centimeters out. On the other side, we have some unknown mass, but we know it's a lot closer, only 8 centimeters from the center. The question is, how heavy does that unknown mass need to be to get a perfect balance?
So to solve this, we use something called the principle of equilibrium. I know, it sounds super fancy, but it's actually incredibly simple. All it means is that for everything to stay perfectly balanced, the twisting force trying to spin the stick clockwise has to be perfectly canceled out by the twisting force trying to spin it counterclockwise. They have to be equal.
So let's build our equation from that idea. The torque on the left side has to equal the torque on the right side. On the left, we've got our unknown mass times its distance, 8 centimeters. And on the right, we have 200 grams times its distance, 20 centimeters. So that's unknown mass times 8 equals, let's see, 200 times 20 is 4,000. Now we just solve for the unknown mass. 4,000 divided by 8 gives us 500 grams.
And there it is. 0.5 kilograms, or 500 grams. And that totally makes sense, right? Because our unknown mass was closer to the center, it had to be a lot heavier to create the same amount of twisting force.
Okay, you ready for another one? Let's flip the script a little bit. This time, we actually know both of the masses. We still have our 200-gram mass sitting 20 centimeters out, but now we're trying to balance it with a lighter mass, only 170 grams. The new puzzle is, where do we have to put it?
So this time, our 170-gram mass is lighter than the 200-gram one. Just using your intuition, where do you think it needs to go? Closer or farther away? Well, to get the same balancing power, it's probably got to be placed farther out from the center. Let's see if the math agrees with us.
We use the exact same principle. Torque on the left equals torque on the right. So 170 grams times our unknown distance has to equal 200 grams times 20 centimeters. That right side is 4,000 again, nice and easy. So to find our distance, we just divide 4,000 by 170.
And that gives us about 23.5 centimeters, or 0.235 meters. Hey, just like we thought. The lighter mass needs to be farther away to balance the heavier one. See? You're totally getting the hang of this.
So far, we've been assuming that all our forces are pushing straight down, nice and neat. But, the real world is a bit more complicated, and honestly, a lot more interesting. It's time to add a new angle to this whole thing.
Yeah, so what if the force isn't being applied perfectly straight down? What happens if you start pushing at an angle? Does that change how much twisting force you're actually creating? You bet it does.
The absolute perfect example of this is a wrench. Think about it. When you're trying to tighten a really tough bolt, you automatically push on the handle at a right angle, right? Because if you push at some weird shallow angle, or worse, if you try to pull along the length of the wrench, nothing happens. The angle is absolutely everything.
So to deal with angles, we need to bring in the full formula. Now, it looks a little intimidating, but I promise it's not. Torque, that's the Greek letter tau, equals r, our distance, times F, the force, times the sine of phi, our angle. Okay, don't let the word sine freak you out. All it's doing is figuring out which part of your force is actually doing the twisting, the part that's perfectly perpendicular to the handle. If you push at a perfect 90 degrees, you get 100% of your force. If you push at a shallower angle, you get less. It's just a way to find the most effective bit of your push.
Let's try it out with the numbers from our wrench example. The distance R is 0.18 meters. The force F is 8 newtons, and the angle phi is 47 degrees. So we just plug that in. 0.18 times 8 times the sine of 47 degrees, which gives us a torque of about 1.05 newton meters. Oh, and one last thing. By convention, physicists say counterclockwise rotation is positive and clockwise is negative. Since our push would turn the bolt clockwise, we call this a negative torque.
So our final answer is negative 1.05 newton meters. That one little number tells us both how strong the twist is and which direction it's going. That's pretty cool.
All right, we have covered a lot of ground here, so let's take a second and pack everything we've just learned into a handy little toolkit that you can take with you.
Okay, here's your new torque toolkit. Let's run through it. First, remember, torque is a twisting force. Got it. Second, for anything to be in balance, the clockwise torque has to equal the counterclockwise torque. Third, just like on the seesaw, where you push matters just as much as how hard you push. Fourth, the angle of that push is critical. 90 degrees gives you the most bang for your buck. And finally, when you're in doubt, the formula is your best friend. Torque equals R times F times the sine of the angle.
And I'm going to leave you with one final thought. You now have the tools to see the world around you like a physicist. So next time you see a door, think about it. Why is the handle placed as far away from the hinges as possible? Now you know the secret. It's all about maximizing your torque.